In this video then we're going to look at trigonometric transformations, which is when you take the parent functions of sine, cosine and tangent and apply various, well, you could say distortions to those standard parent functions. Okay? Now before I do so, I should just recall that in the previous video where we drew out these diagrams, there's a small mistake, and I just want to correct that mistake before we go forward. The mistake, which is just maybe I just didn't explain it sufficiently or extend it far enough, is in this area of the tangent functions. And you might have been screaming at the screen that I haven't done the same on the left here as I have done on the right. And I should have done. What I should have done is something like this. I should have extended that hypotenuse to hit a vertical line here, which I've drawn in now. And that means that my opposite should actually have been, my opposite side should have been drawn in here, so it would be a rather larger size. Now that's if, of course, we are keeping our cotangent fixed. In this case, keeping it fixed at -1. So the hypotenuse then is the one that gets stretched, and that gives us this height for our opposite side. And what is that height? Well, the height of the opposite side is going to be the same as the height over here. So in other words, 1 over √3. Okay, or √3 over 3. Now, that really wasn't such a big problem until you start to think about what happens when you go into the negative. When you go into the negative, sorry, not when you go into the negative, when you go into the third quadrant, when you go into the third quadrant like this, what's going to happen to the adjacent and the opposite sides? Well, I said that it would stay in the negative, and that's true, that obviously the adjacent side will remain negative, but the opposite will go into the negative as well. And this is what I didn't explain. So let's use a red pen for that too, and now draw in the opposite side of this reference triangle. Okay. Now in this case, what's happened then to the tangent is that it's become a negative divided by negative. In other words, let's have a look. The opposite side has become -1 over √3, and as we can see, we've got a -1 for the adjacent side. So opposite over adjacent means we're going to get a value of not -√3 for what is this, 210 degrees. 210 degrees is going to map onto well, -1 is -1 over √3 is the opposite, divided by -1 will give us a negative divided by a negative. In other words, 1 over √3 or √3 over 3. Okay, so I hope that's clear. What's happened is a negative divided by a negative has produced a positive again, and this is really, really important. It's very important for what we're going to look at today. If in the third quarter, or third quadrant, I should say, everything has gone positive again, it's exactly as if we've popped back to where we were over here. Okay, so now we're starting our journey again, and it's going to be exactly the same, this journey, as it goes around like this and like this. As it goes around, it's going to have all the same values, and everything that's happening to this ratio, to the function, I should say, is going to be the same as what happens here. So if that's the case, we say, well, instead of it starting, continuing round in a full revolution, as we get with the sine and cosine functions, in fact what's happened is it started again. And we call this the period. Okay, so we call this the period of the function. Just write Fn. So the period is our starting idea for today, because as we've seen, let's just use a different colour here. If we think first of all of the sine, cosine and the secant and cosecant functions, well, they must have full 360 degree periods. So the period, in other words, equals 360 degrees for those four functions. So let's just draw that like this. Round we go, keeps going round into the third and fourth quadrant until the cycle begins again. But for the tangent and the cotangent functions, the period must equal 180 degrees, which means, if we draw what happens again, that we start here, we go through the first quadrant, the angle increases and increases to 180 degrees, but we stop there, go back to the beginning, it starts all over again. So the period is only half a revolution. Okay, so we're going to have a look at the period now, but we're also going to look at how we sketch, in a much simpler way than we did in the second part of the video last time, these trigonometric functions, especially when they move into transformations. So we're going to start with a new problem, which is actually an old problem. Let's just call it problem A, and say we're going to have to sketch, just sketch the f of x, so function in terms of x, of y equals sine of x. Okay, what does that mean? Well, let's just draw some axes actually and show you what it means on axes. If we've got a y and x, then we must have a y and x axis arrangement. So they want us to write the angle, they want x to represent the angle, which we usually think of as theta. So it can be confusing because very often on an xy axis what we're doing is drawing, say, triangles or rectangles and looking at areas. In other words, the x-axis would be a length, it would represent side lengths, but here that quantity x is going to represent our angles. So that's our input. We input an angle, and our output here, what comes out, is the y value. So the y value is the ratio. Okay, so that's our output. Okay, so what are we going to do with the sine function? Well, the first thing we need to recognize is that the sine function has a period of 360 degrees, as we've just seen. So if we've got axes drawn like this, then we have to end our axis here in the positive direction at 180 degrees. That means we're going to extend back to negative 180 degrees, so that the difference between negative 180 and positive 180 gives us our period of 360. Now, if that sounds a bit confusing, what's a negative angle? Consider again this idea of a circle. So going round and round, opening up that angle as it goes round and round. And if I went 3/4 of the way around, so 180 to here, 90 to here obviously, but if I went down to here, that would be 270 degrees. Okay, what would minus 90 degrees equal? Well, if positive 90 degrees is in this direction, so that would be 90 degrees going in anti-clockwise direction, then minus 90 degrees must be going in a clockwise direction. So 270 degrees equals minus 90 degrees, They're the same thing. So when on my graph I say minus 90 degrees, I also mean 270 degrees if we were going in an anti-clockwise direction. And minus 180 degrees, well, if we think about it again, positive 180 degrees is going in this direction all the way around, well, half the way around rather, to 180 degrees. Then going in a negative direction 180 degrees will give me also, will take me also to the same point, so 180 degrees must equal minus 180 degrees. And that makes sense if you think about our period, because what's going to happen when it completes its period is it's going to jump to here, or if you want to think of it the other way around, it will jump to here. So this is a full period. We're going to see a full cycle of this function going from this point here, whoops, to the opposite side at positive 180. Okay, so let's also just erase these workings and just keep it nice, simple. In fact, I'm going to even erase my 90-degree markings to make it nice and clear here. Okay, and then just put a mark here at 90 degrees. Now that's going to be sufficient for our sketch. Now the next thing, or the final thing really we want to think about, is the amplitude, and I'm going to use a different colour for that so that it stands out. So what's going to be, we've worked out our period, well that's going from here to here. What's going to be our amplitude? In other words, how high is it going to go? Well, we've seen that the sine function extends up to 1. So I'm going to, well, let's use this mark here. Okay, so the highest our function can reach is a y value of 1. Okay, and the lowest is going to be a y value of negative 1, like this. So negative 1 will be here. So our amplitude is, it's not the total distance from here to here, rather it's how high up does it go, how much does it depart, you could say, from the baseline. Okay, so if the baseline is this, is the horizontal x-axis, then how far up or how far down does it go? The answer is it's got an amplitude of 1. Okay, and that's all the information you need to sketch a graph. Okay, so once you've worked out the amplitude, the period and the amplitude, then you can go ahead and sketch. So the sine function starts at 0, so at 0 it is 0. At 90 degrees it goes up to the value of 1. So the sine of 90 degrees is 1. And if we wanted to think about our half values, then it's going to be root 2 over 2 at 45 degrees, so they're about there. But we should know the shape of our graph, so it should be fairly straightforward to, let's put in our lines here, simply draw it up like this. Okay, and that's completed half of the period of the sine function. Then we go in the opposite direction, so at minus 90 we know we're going to get an output of a minus 1 here, and then again it's a simple matter of just joining these lines up like this. Okay, make sure we've got no gaps at all, and there's our sine function like that. Okay, so that's completed problem A. Problem B. F of x equals, well, let's just say the cosine of x. So y equals the cosine of x. So our period is going to be 360 degrees, and exactly the same as the sine function. We can draw it on the same graph, because if the period is 360 degrees, the amplitude is also going to be 360 degrees. So let's write amplitude, okay, equals 1. So again, it's the distance up and the distance down it goes, if you like, on the y-axis. So it's how far does it depart from the baseline. Let's use a red pen for our cosine function then. And let's see, well, let's start with 0 again. When we input an angle of 0, the cosine of 0 is going to be 1. Okay, so again we can mark it on our graph here. If we go to our 90-degree value straight away, we know that's going to be a 0, so nice and easy. And we know as well that sorry, that's disappeared there, hasn't it? There we go. At 180 degrees, it's going to be -1. Okay. And if we just jot in our interim values here, it's going to actually cross the sine function here, √2/2, and reverses in this direction to get to 180. So going in the opposite direction, we have -90. The cosine of -90 is the same as cosine of 70, and it's 0. So we can join up to that point there. And the cosine of -180 is the same as the cosine of 80, so it's going to be -1. Like that. So that's completed problem B. Okay, let's make it a little harder. Let's have, whoops, wrong colour. There we go. This time, let's distort our function a little bit. So this is what we mean by transformation. So far, all we've done is sketched what we call the parent functions. So the sine, the cosine, the tangent, the cotangent, the secant, the cosecant, these are all parent functions that can be transformed, and they can be transformed in about 4 different ways. We're going to look at 2 in this video. Okay, so let's just distort our sine x value by putting a 2 in front of it. It simply means 2 times the sine of x. So 2 times our parent function. So what's the period going to be now? Well, the period is still 360. That doesn't affect the period at all. Actually, let's give myself a little bit more room here. So y equals 2 sine x. There we go. We just need to bunch it up a little bit more. Y equals 2 sine x. Period is unchanged at 360 degrees. But what has been changed is the amplitude. And I'm going to show you what I mean. If I draw another pair of axes here, what we've done is we've doubled any value that we're going to get back. Now, what is the value that we're going to get back? In other words, what's the output value? It's the value on the y-axis. So it's the y. So if we've doubled the y, then 1, which was the amplitude, is now going to become 2. So the new amplitude, like this, is going to be 2. So the amplitude when y equals 2 sine x equals 2. Okay, and if that means marking off 2 on the y-axis, it also means marking off -2 down here. But the period has remained between minus 180 degrees and 180 degrees, like that. Okay, now it just remains for us to draw our graph. Well, if we think of 0, 2 times 0 is going to be just 0. If we go to 90 degrees, where normally the output value, the ratio, is going to be 1, then now it's going to be 2 times 1 equals 2. So that's going to be up here. Similarly, if we go into the negative here, when, well, let's go to minus 90 or 270 degrees, then we're going to have a period of a y value of minus 2, and then we've got our zeros like this. Okay. And again, we could just put some little guide lines here at our 45 degree. Don't have to do that, but it's quite a nice thing to do. You can then almost see the curve before drawing it, and then drawing it with a continuous line. If you can not take the pen off the paper, then that's going to ensure that you get a continuous line like that. So I'm reasonably happy with that. Let's move on to problem, well, our D problem. Okay, so now what we're going to do now is distort or transform our function even more. Let's have 2 sine of, in fact, why don't we just make this even, let's just make it a little different. In fact, let's change it to 12. Okay, then you'll really see a stretch on that y-axis. Okay, 2 sine x, but this time what we're going to do is do something to this x. So instead of just plain old x, we'll have, well, let's say 2x. Okay. Now we've really changed this. So we've got our new function is y equals 12 sine 2x. First thing we need to ask is, what's our period going to be? Okay. Well, our period so far for the sine function has been 360, and you can guess that this time this is going to distort that period. Now, why is it going to distort it? Let's just think about this for a moment. If I now am talking about 2x, okay, so my angle is, so sine of the double of my angle, okay, sine of 2 times my angle, then it's basically going to take me, each time that I take a reading, I suppose you could say, it's going to have gone around that circle twice as far. All right, as it's going around, let's just do it on here. As it's going around that circle, it's doubled because it's times 2. So each time I take a reading, it's going to be twice as far around that circle. I hope that makes sense. Okay. Now, if that's the case, then it's going to get around the circle. In other words, it's going to complete a full period twice as quickly. So the period now is going to be half of what it was. So what this gives us is a period of a half. So the 2 is actually going to be a half of what our period usually is, which is usually 360. Okay, so you could say that to calculate, there we go, to calculate the period now, we just take the period of the parent function, so 360 degrees, and divide by this coefficient of x. So the period now becomes 360 divided by 2 equals 180. Okay, so now how would we draw that? Well, we need a new set of axes. If the period is 180, we can, okay, if the period is 180, we now need to set this at 90, okay, and this one at negative 90. Now we might have done it differently, we might have stuck with the 180, but because we want to use all of the space, we're going to start 90 here and not bother about what goes on up here. Okay, otherwise we'd have to draw the same period twice. So now let's have a go at the amplitude. Well, what's the amplitude going to be? The amplitude. Well, as we've seen, the amplitude is very straightforward to calculate. It is simply this value here, the amount that we're multiplying the whole thing by. In other words, 12. So the amplitude is 12, therefore we need to mark off on our axes 12, and down here, negative 12. Now we're ready to draw our function. Well, it's going to be exactly the same as we had before. It's simply that we've changed our values on the x and y axis, but the sine of 12 times the sine of 2x is going to look exactly the same. Okay, so it's going to go through 0 here, it's going to have this shape here and here, and if we draw it round, you can see that we've got exactly the same thing as we had before. So when we're curve sketching like this, we really don't need to worry too much about the values. We're concentrating much more on the shape, and we get the shape by doing a little bit of work beforehand, defining the period and the amplitude. Okay, let's move on to, well, let's have one final problem. F of x equals, well, why don't we just, let's just add a negative. In other words, multiply by -1. So y equals now minus 12 sine of 2x, where, well, we've got to work out our period. Okay, and we're also going to work out our amplitude simply by adding a negative. What change did that make? Okay, amplitude. Well, if we're multiplying by -12 this time, then every time we've got a value like 12, for example, that will be -12, in which case it's going to be plotted down here. Let's use a different color actually. This time let's use green. Okay. At 0, -12 times 0 is going to be 0 again. At 90 it's also going to be 0. At -90 it's going to be 0. But here, -12 times -12 is going to give us a positive. Okay, up here. So in other words, what happens, okay, so it's -1 times -12. So what happens, as you can begin to see as I draw it up, is we get a reflection. Okay, let's mark our 45-degree points here. And this will always happen for any function. So if we have a negative multiplier in front of the function, we're going to have this sort of flipped curve, you could say, which with the sine function is going to look like that. So you need to look out for several things when you're given problems like this. First of all, you need to have a look at this term here, because that's going to give you the amplitude. Okay, the amplitude. Whoops, wrong colour. Here we go. So in this case, the amplitude, well, it looks like it's going to equal 12, and in a sense it does equal 12. Well, it does equal 12. Let's just see why that's the case. We might be tempted to write -12, but let's have a look at our graph. Remember, the definition of the amplitude is how far it departs from the baseline. And in this case, it's departing by 12, just in the same way as when it was in the positive, it was departing by 12. So flipping it doesn't change the amplitude. Another way of thinking about this is by talking about the absolute value. Okay, so we have a look at the absolute value. The absolute value is the length regardless of whether it's positive or negative. The absolute value. Okay, but the negative does have an impact, as we've seen. So having a negative is the second or third thing that maybe you want to look at, probably the second thing. Okay, so has it got a negative? If it has a negative in front of it, that's not going to affect the amplitude, but it is going to flip it about the x-axis. So let's just write that as flipped. Okay, but remember it's flipped about the x-axis. Okay. All right, and then the final thing that you want to look at, if we just summarize all of this, is this value here. Is there a coefficient in front of the x? Now if there is, it's going to halve, in this case, the period. So we found that the period here was, let's see, as it was in problem D, was 180 degrees. Okay, so you take that value, you take the parent period, you divide by that value, and you're going to get this period. If it was a half, for example, okay, let's just think about if that was a half, sine of half x, then what would happen? That would then double the period, and therefore the period would equal 360 divided by a half is going to be times 2 equals 720. So that would be another problem that we could look at. But that's the basic idea. So you take your transformed function, you have a look first at this multiplier in front of the function. You then want to think, well, if it's got a multiplier, then its amplitude is going to change by that same amount, but it's not an amplitude, we need to be careful here, of minus 12. It's the absolute value, which in this case is 12. But you do want to take account of that negative, because that's going to tell you whether the curve is flipped or not. And finally, you want to have a look at the coefficient of x, because that's going to tell you about the period. Okay, well, that's the idea, but I think what you want to do now is to practice some curve sketching, and again, there'll be a video to help you do that. Now, just a couple of things to say at the end of this tutorial. The first is that you should play with a graphing calculator. The reason for this is that the graphing calculator will instantly draw the graph, which will allow you to input all sorts of values very quickly and be able to make very straightforward, very quick comparisons. Now, the sort of comparison that I have in mind, I've given you here. This is looking at the tangent function, and the first thing we'll notice, and it's an interesting thing to think about, is that there is no amplitude as such. So if I take my baseline here and ask myself, well, where's the peak of this function? It just doesn't have a peak. There are no peaks and troughs. So in other words, the graph extends towards infinity in that direction and towards negative infinity in that direction. So if it has no amplitude, let's just write amplitude question mark. Does it make any difference if I increase this value here, which I've done in both cases. So I've increased my tangent function, my parent function, by this absolute value of 12. Have a look for yourself and see what changes it does make. You could try increasing it by an absolute value of much higher, 50, 100, 1,000, to see whether you can notice any change in the function. But that's an important one to experiment with, because it's an important difference between the tangent and the cotangent and the other functions. So now the main reason to show you this slide, though, is because of the changes that we've made here. Now, in this graph below here, which is a flipped graph because of the negative, okay, so you should see it's drawn the line in the opposite direction to how it's drawn it up here. But I'm not looking at that at the moment. I'm looking at the coefficient of x. Now, there's no coefficient of x here, so I'm expecting what? A period of, well, it's just 1. So it's 180 for a tangent and cotangent, divided by 1. I'm expecting a period of 180 degrees. Let's have a look. So if we start our examination here at the 0 on the x-axis, and just draw a range looking at the graph and thinking, well, I'm now halfway, okay, because it's gone in this direction, then it's gone down towards the asymptote, and then it's appeared back up here, so it keeps going, but just in this direction now. So if I keep drawing my range line here, there we go, it's going to complete there. And a good test is, well, if it completes there, then it must restart here, and sure enough it does, and it begins to go down again just as it did before. So that's exactly what's going to happen here. Now you can see that even more clearly if I start at the asymptote here and draw my range across like this. So there's 90 degrees. Keep going to 180 to my second asymptote here. And again, have a look what's going on with the graph. It's then going down, tending towards infinity, and so it's going to reappear here, and sure enough it does the same here as it does here. It starts again. So I can be certain that it's drawn it correctly. In other words, I've got a period of 180. Now up here I'm expecting what? I'm expecting a period of 180, because tan and cotangent have a period of 180 in the parent function, but this is a transformation, and the coefficient is going to give it a period of a third of 180 equals 60 degree period. Now if I have a look at 0 here, let's just go any arbitrary length up here, so it's starting at x equals 0. What I can do is say to myself, well, where is 60? It's going to be a third of 90, so something like that. Okay, draw my line, and again have a look at what's happening to the graph. Well, the graph does its switch here, and it does its switch here. So if I have a look at what happens to the graph, okay, and then it reappears here, sure enough it's going to repeat exactly what it did here. So off it goes again. Okay, so I hope that's helpful, and I hope what I've done is encourage you to play around with these sine functions, because with these trigonometric functions, because the more you play with them, and the graphing calculator is an extremely useful device to help you enjoy playing around with them, the more you play with them, the more you'll become very familiar with how these trigonometric functions work.